Good afternoon, everyone, and thank you all for being here. We are Team 4, and today we will be presenting our final design for the City of Watertown treatment plant as part of CIEN 412. Over the past several weeks, and we have developed a complete and functional design for a treatment plant capable of producing more than 11 million gallons of safe drinking water per day. Our presentation will walk through our design basis, the selected treatment train, key design calculations, and the overall performance of our system. We'll also show how our design meets not only federal, but state regulatory requirements while remaining practical and cost effective for the city. My name is Martin Spinner.
My name is Kayla Alexander.
And my name is Marcel Gillespie. So with that being said, we're going to get into the actual project overview. So Watertown's population is growing and its current treatment system can't meet its current increase in demand. So especially during the peak water and uses for fire emergencies. So we designed a new facility capable of reliably providing 11.21 MGD. And then since the water source is a surface water, it presents challenges such higher turbidity, seasonal quality, challenges like pathogens like Giardia, and then like hardness, which can affect the overall taste and the plumbing.
This slide will summarize the most important water quality parameters. A turbidity level of 9 NTU means the water contains suspended solids that must be removed prior to filtration and disinfection. The water is also very hard at 255 milligrams per liter, which requires softening. Because we detect coliform bacteria and Giardia cyst, the treatment plant must include processes that provide both physical removal and disinfection. The raw water pH and temperature were also considered because they influence chemical treatment performance and CT requirements.
So, this is the overall treatment train that our team has selected. Each step plays a very important role in achieving final water quality. So, the screening kind of removes the debris throughout the process. Rapid mix introduces aluminum quickly to destabilize particles. Flocculization allows the destabilized particles to form larger, settable flocks. Sedimentation removes the majority of the solids before the water enters the softening stage. Lime softening reduces the hardness and improves the overall water stability. Moving on to dual media, which actually filters and provides the final particle polishing. The UV disinfection ensures the 4-log Grada inactivation, and chlorine provides a lasting residual, residual, in the distribution system. And then finally, pH stabilization prevents corrosion before the water is stored and distributed.
So next we'll be getting into the coagulation and rapid mixing. So we selected a dose of 40 milligrams per liter, which is typically for water with moderate turbidity. So rapid mixing is ultimately essential to ensure the uniform distribution. So utilizing a 1 minute detention time and a plant flow rate, we calculated a required rapid mix volume of approximately 1,040 cubic feet. And then now we'll be getting into the actual design.
So for the design, the purpose of flocculation is to gently mix the water to allow flocks to grow large enough to settle. Based on standard design criteria, we selected a detention time of 25 minutes. With the plant's flow rate, this results in a required total volume of 26,010 cubic feet. Assuming a depth of 12 feet, the required surface area is about 2,168 square feet. These dimensions fall well within typical values for municipal plants and ensure proper mixing conditions.
Sedimentation is one of the most crucial steps for removing solids. Using a surface flow rate of 900 gallons per day per square foot, which is the standard for rectangular clarifiers, we calculated a required surface area of about 12,457 square feet. With a depth of 10 feet, this gives us a detention time of roughly 2 hours. To provide operational flexibility and ensure reliability, we propose using 4 identically sized clarifiers. This setup ensures the plant can continue operating effectively even if one unit is offline.
So now the lime softening is necessary because of the ultimate high raw water hardness. So we aim to reduce the hardness from about 255 milligrams per liter to below 120 milligrams per liter, excuse me. So rising pH helps precipitate calcium and magnesium, which ultimately removes the sludge. That being said, this softens the water and improves the solid removal and enhances the downstream filter performance.
So for the filtration system, our system consists of dual media filters designed to remove any remaining suspended solids. Using a loading rate of 4 gallons per minute per square foot, the required surface area is nearly 2,000 square feet. With each filter providing 300 square feet, we determined that 7 filters are required in operation, along with one standby filter. This ensures continuous filtration even when a unit is backwashed.
So, because Grenada is resistant to chlorine, the UV disinfection is used to achieve the required 4-log removal. We selected a UV dose of at least 40 millijoules per square centimeter. Chlorine is added after filtration for providing a stable residual in the distribution system. The clear wall provides about 45 minutes of detention with a baffling factor of 0.5. Our effective contact time results in a CT value of 22.5, which is sufficient for bacterial control.
So this slide shows the estimated operational cost. So electricity is the primary cost driven by pumping and a UV disinfection. Alum is the second highest cost because of the large volumes required for coagulation. And then chlorine has a relatively small annual cost combined to the total operation and maintenance is just over $700,000 per year, which is the reason for a plant at this capacity.
So for sludge and residuals, the plant will generate three main types of residuals: alum sludge, softening sludge, and filter backwash. These solids must be managed in compliance with environmental regulations. We recommend gravity thickening followed by centrifuge dewatering. This produces a manageable sludge volume that can be disposed of or further treated according to the city's needs.
And finally, our final water quality meets or exceeds all federal and state regulatory standards. Turbidity remains below zero point 0.3 NTU. The hardness is reduced to the target level. The microbial safety is achieved through UV and chlorine. We also maintain a stable finish pH to minimize corrosion in the distribution system.
So now the team responsibilities. And to complete this project, our team worked collaboratively, but also divided responsibilities on strength, excuse me. So Kayla handled the report organization and overall presentation quality. I focused on coagulation, sedimentation, and the softening process. And Martin covered the filtration design, disinfection, and all chemical and energy calculations.
In conclusion, the proposed treatment plant meets all regulatory requirements while providing reliable, softened, and safe drinking water for the city of Watertown. All unit processes were designed using standard engineering criteria, and the plant has built-in redundancy to ensure continuous operation. Our design is ready for further refinement in future engineering phases. Thank you for your time.